Hello, this is problem set number 4, problem 4. A 15 kilogram block of ice at 0 degrees Celsius melts to liquid water at 0 degrees Celsius inside a large room at 20 degrees Celsius. Treat the ice in the room as an isolated system and assume that the room is large enough for its temperature change to be ignored. Part A is a melting of the ice reversible or irreversible. Explain using simple physical reasoning without resorting to any equations. Part B, calculate the net entropy change of the system during this process. Explain whether or not this result is consistent with your answer to part A. Okay, so to start off, I'll write down my givens. I know that the mass for the block of ice at 0 degrees Celsius, which is actually also the mass of the melted liquid water at 0 degrees Celsius. Notice the temperature stays constant, 0 degrees block of ice and 0 degrees melted water. But the mass of that is 15 kilograms. Okay. It said treat the ice in the room as an isolated system. So isolated system that means our system plus surroundings. All right. Okay, and then the temperature, assume that the room is large enough for its temperature change to be ignored. So the temperature of the room is constant at 20 degrees Celsius. And the temperature of the ice, which is actually also the temperature of the water that melts, is also constant at 0 degrees Celsius. Okay, I'm just going to change that to Kelvin just to make it easy on me so I don't have to do that later. And to do that from degrees Celsius to Kelvin, I just need to add 273 to the temperature I have in Celsius, and then it'll be Kelvin. So for 0 degrees Celsius ice, that will become 273 Kelvin. And for the 20 degrees Celsius room, that'll be 293 Kelvin. Okay. All right, so part A is the melting of the ice reversible or irreversible? Explain using simple physical reasoning without resorting to any equations. Okay. I'm going to say that the melting of the ice is irreversible. Okay, so the melting of the ice is irreversible because the temperature of the room is 20 degrees Celsius, right? So in order for the melted water at 0 degrees Celsius to turn back to ice, we would have to freeze it back to ice, but in order to do that, we would have to add work. Work would have to be done on the system to transform the 15 kilograms of liquid water to ice, to a block of ice. Okay, so the melting of the ice is irreversible because the temperature of the room is 20 degrees Celsius. So heat won't just leave the 15 kilograms of 0 degrees Celsius water and freeze it back to ice. Without work being done on the system. Okay? So that'll be my answer for part A. For part B, calculate the net entropy change of the system during this process and explain whether or not the answer you get for the net entropy change is consistent with your answer to part A. All right, well, real quick before we do that, a reversible process occurs with zero entropy change, right? Since the entropy change of the system is going to be matched equally by the opposite entropy change of the surroundings, right? So it's going to cancel out. So the net entropy change is going to be zero for a reversible process. Okay, so for a reversible process, the entropy change is equal to zero. Okay, that's a net entropy change. And for an irreversible process, the net entropy change is going to be greater than zero. So let's calculate the net entropy change of our system during the process, and hopefully it will agree with my answer that it is an irreversible process. And so hopefully the net entropy change would be greater than zero that we calculate for. Okay. So for part B, we're looking for the net entropy change, right? What is, again, we are also told that we are going to treat the ice in the room as an isolated system, right? Treat the ice in the room as an isolated system. So therefore, my net entropy change will be the entropy change for the ice that melts, as well as the entropy change of our surroundings or the room. Okay. So, what is the formula for the change in entropy, right? So this is a side note, but the change in entropy is equal to Q, which is the heat added to the system, divided by T, which is the temperature at which the heat is added, okay? So this is the change in entropy This is the heat added to the system. And that is the temperature at which heat is added. Okay. So what is the heat transfer necessary to change phase? Because that's what happens here, right? The ice melts. The ice is at 0 degrees Celsius and it melts to liquid water at 0 degrees Celsius. Notice the temperature does not change from the block of ice and the liquid water, right? So then I won't have to worry about the heat transfer of a system within the same phase due to temperature change, because there was no temperature change. And that's mc delta T, right? Q equals mc delta T. That's a heat transfer associated with temperature change within the same phase. I don't have to worry about that because my temperature remains at 0 degrees Celsius. What I do have to worry about is the heat transfer necessary to change phase, right? To melt the block of ice into liquid water. So again, We covered that in chapter 17, but the heat transfer necessary to change phase, right? That is equal to plus or minus m and the latent heat of fusion, because we're going from solid to liquid, right? So that is the heat transfer necessary to melt that block of ice to liquid water. Okay. Okay. So let's write that down. The change in entropy, right? That is heat added to the system, or Q, over the temperature at which the heat is added. In our case, for the ice, Q, we just need the heat transfer, or the heat necessary to change the phase, to melt the ice. That is the heat added to the ice that melts it into water without changing temperature. So the ice and the water are both 0 degrees Celsius. That's what the problem states. So do I choose positive or negative right here? Well, because I'm going to add heat. Heat is going to transfer into the ice to change the phase from solid to liquid. That's going to be positive, right? So positive, my mass is 15 kilograms, right? That was given in the problem. Times the latent heat of fusion, and the latent heat for fusion for water is 3.34 times 10 to the 5 joules per kilogram. Okay? And I'm going to divide that by the temperature of the ice, and in this problem that's constant, so that is 273 Kelvin. Okay. Again, this problem is associated with this, okay? That's a change in entropy for the ice. Okay. What about the change in entropy for the room? I'm just going to move this a little bit to the left so I have more space. Okay. Well, understand that the heat transferred into the ice, or Q ice, right? That's a heat transferred into the ice to melt it to water. That's going to be equal in magnitude but opposite in sign to the heat that leaves the room. Because the heat that transfers into the ice right there, that's heat that comes from the room, right? So heat leaves the room and transfers into the ice. Okay? So Q room will be equal in magnitude to this, the heat transferred into the ice, but it will have a negative sign, or the opposite sign, right? So the sign is going to be negative because heat is going to leave the room and transfer into the ice. So it leaves the room. The room is our system in this case, right? And just the same magnitude as whatever transfers into the ice. So that's 15 kilograms times 3.34 times 10 to the 5th joules per kilogram. Okay? I'm going to make this much smaller. Okay, and I'm going to divide that by the temperature of the room. And that is 293 Kelvin. If you're wondering where these came from, I'm using this equation right here. delta S is equal to Q over T. Okay? And basically delta S ice is equal to plus the mass of the block of ice times latent heat of fusion, which we use for water, right? That's to transfer or to transition water from a solid to a liquid or a liquid to a solid, divided by the temperature of the ice. And for this guy, the change in entropy for the room, that is equal to the same magnitude of whatever heat transfer entered the ice that just left the room, but it's negative because it leaves the room. And we divide that by the temperature of the room. Okay? So these two equations come from that. All right. So back to the problem. I plugged this in my calculator, cancel out my units, and I'm going to get that the answer is 18,351.65 joules over Kelvin minus 17,098.98 joules per Kelvin. And so my net change in entropy is equal to 1,252.67 joules per Kelvin. All right. That is the answer for part B. That is calculating the net entropy change of the system during the process. But I'm also asked to explain whether or not this result is consistent with my answer to part A. So in part A, I said that the melting of the ice is an irreversible process, right? And I got that the change of entropy is positive 1,252.67 joules per Kelvin. And like I said earlier, for an irreversible process, the net change in entropy should be greater than 0, which here our net change in entropy is indeed greater than 0. So that confirms my assumption in part A, or my answer in part A, that the melting of an ice is an irreversible process.